Hey, Kevin.
Not going to let you off the hook.
No, you're not. This is it now. You're talking about a celebrity. There we go.
All right.
All right.
We still have some people trickling in, but yeah, go ahead, Heather, please. Start it
Yeah, we'll
off.
go ahead and get started. As hopefully everyone on the call knows, we're going to be talking about the generics draft proposal tonight with the infamous Bill Kennedy. And so very excited to dig more into that and get a better understanding. Thanks, Bill.
Got it. So let me set up some ground rules and what I'm attempting to do for the next basically hour and a half here. And trust me, this time's going to go by fast. My goal with all of these meetups is to try to introduce the new syntax that's being presented in the current draft document. And because a lot of us are very, very busy, we don't have time to read that draft. We don't have time to experiment with it. But the syntax that we're choosing is so critically important because once it's in, it's in. And it's really important that everybody who wants to have a voice in this conversation gets to have it. Now, what I just put into the chat window are 3 links there. One is a link to the repo with the code that I'm going to share. I'm going to share my screen soon and we'll see that. The other one is a link to the actual draft document. And then the last one is a link to a Google survey that the Go language team that's working on this can see. And that link is really there for those of you who want to share feedback and opinions without it turning into a public debate. It's also an anonymous survey. So it really gives everybody here an opportunity to express thoughts, opinions, ideas. And if you're like me, I'm always nervous talking on the mailing list and in GitHub. So it's a great opportunity to get that feedback. Okay, so again, my goal is to introduce you to as much of the new draft syntax as I can in basically about an hour, and lately it's been about an hour and 10 minutes. That time's gonna go fast, so I'll be marking the clock in a second. Then once I'm done with that, I'm gonna open up the floor and give everybody an opportunity to ask questions or comments. We are a fairly small group, 32 people, oh, look at that. So we'll have to be, we'll see how we do that at the end. So I'm not gonna be taking questions during my talk. I won't get through it in the hour that I have. That being said, and we're lucky to have Kevin in here who knows and taught me just about everything I know. We've got Corey in here, who again is a Go expert. I want you to use the chat window while I'm talking to discuss between yourselves everything that I'm sharing. Use that opportunity over the next hour to have that conversation. And I'm sure Corey and Kevin and others in here who are familiar with the draft can basically help with any questions you have as well. So I won't be able to look at the chat. I'm not going to be looking at it for questions. But once I'm done, then we can go off and questions and comments. I'm really interested in your thoughts and ideas. Okay. One more thing before I switch over to my shared view here. I need you to appreciate right now that this syntax we're about to see has not been implemented at all yet in the compiler. What we have is a tool called Go2Go, which is transpiling the new syntax into Go syntax that can actually be built and run. So I just want you to be aware that this really hasn't been implemented outside of this tooling. And in a couple of cases that we'll see over the next hour, there's even aspects of the draft where there is syntax that's legal, but it hasn't even been implemented yet in the tooling. And that's actually fair because I don't think we really want the Go team spending all their time making the transpiler complete. We really want to get to a point where we're happy with this syntax and we can start putting it into the compiler. All right, and I'll point out places where it's really not, it won't transpile even though it's legal. So we'll talk about that. And then my goal is to really try to help you understand why we even need some new syntax at all. Okay, so I'm going to go ahead and share my screen. Beautiful. We're on my repo here. I'm marking the clock right now at 45 minutes after the hour. 45 minutes is my marker, and we should be done within an hour, hour and 5 minutes. Now, on this repo here, I moved you right to the generics. This is all of the code that I've written over the last couple of months to help people understand and learn the draft. Now, there is zero way we can get through all 12 of these. I'm not even going to try. My goal is to get through the first 5. If we get through 5, which we will, then you've seen, I think, at least 80, maybe 85%, if not more, of the draft syntax. At least right now, that's important. And then the rest of those examples, you can go ahead and look at yourself and experiment with. And again, I'll give you my email address when we're done. So we always have, you have questions and stuff. Now, in the README for this folder here, you'll see a link right over here that will give you access again to the draft document, the same link that I provided to you in the chat window there. You can see it was updated actually today. So that's kind of cool. Here's a link to the Go playground, a special playground they put in that runs the transpiler, the Go transpiler. If you end up having questions, which is very, very code related, it would be brilliant if you can use the playground and then we can share those links at that time, or you can share those links amongst yourselves while I'm talking as well. So leverage this. You have access to the code from the other link, the repo, so you can copy and paste and do your thing. So really helpful, and then I can share that as well. Now, I'm not going to read this because we don't have time, but you can briefly scan this. I stole this from the draft document. This is the current high-level overview. This is what is currently currently slated as what would be part of a first release of generics in Go. This is what the draft right now is focused on, okay? It doesn't mean that this is necessarily the final list for the release, but at least right now, this is all I can really show you in terms of where the draft is right now. This right here, again, I'm not gonna read it, is currently what's being omitted from the first release. Now, notice I just said first release, okay? That doesn't mean that at some point in time, Go may have these things, but right now, that being said, it's a living document. If somebody comes up with the most perfect reason why we need specialization or metaprogramming, then they're going to focus on it. But right now, it doesn't seem like these things are needed, say for a first release, which always brings up the question, well, Bill, when are we going to have this first release? Well, I need to stress quite a bit here that I don't work for Google and I'm not on the Go team. But we just released 1.15 of Go here in August, and we do 6-month releases. And so the next release, 1.16, would be in February, and then 1.17 would be in August. I would think that the earliest possible case that you might see a compiler implementation of this would be 1.17 in August, though I really think you're looking at the February release of 22 as probably a place where this could land. That's my guess. This is Bill guessing. Okay, if we were in Vegas and I had odds, that's where I put my money. February of 22 at 118, 67, 18 release. Okay, doesn't mean it can't come sooner, but there's still a lot of work that has to be done. We're just focusing on the syntax tonight. All right, and that's it. Now I do got some special links here if you want to read more, and I'm not going to be using the playground. So I've got instructions here that will teach you how to download the Go source code and then go into the Go branch and then build that out. And in fact, that's what I did yesterday. I didn't get a new version today, but I did that yesterday. And if you see me type Go version, you'll see this does not say 1.15, but it says a release from yesterday, August 26. There it is. So I'm going to be running this locally here. Again, we're going to use that Go transpiler. Okay, with everything I just said here, marking my clock, I said, I'm going to look at it again right now. 7:50 on my time, 50 after the hour. That's it. That's my marker. Here we go. We're going to jump right in. Now, if I'm having any audio issues, if I'm having any video issues, someone is to chat, and then Heather or Warren, please, please, please interrupt me and say, Bill, we can't hear you. Bill, we can't see your screen. If it's not legible, if the fonts are not large enough, you must speak up. Interrupt me, please. And we will fix that, okay? Because I'm blind and I really can't see. Now, we're gonna go through the first 5 examples here. This is what we need to do. And I'm going to be here in Visual Studio, that Visual Code. Here we are. Let's get into it. Now, in this first example, what I'm really wanting to do here is kind of walk through a progression of the current syntax we have today, the new syntax that we're proposing, and even why we need a new syntax. And then from there, we'll move on to more and more examples. So let's jump right in here right now. So if you look on line 13 right there, you can see that I wrote a function called print numbers. Now the idea of print numbers is to accept this collection of integers via our data structure, that slicing data structure we have in Go. And you can see the 5 lines of code that I've written to do this printing, right? I've just got a header, I've got a carriage return line feed at the end, and then I'm using our for range mechanics here to do that linear traversal across that collection of integers, and I'm using the print function there to display those ints. 5 lines of code, we can do that. And I'm going to make a bold statement right now. I'm going to say that I believe that all Go developers, even if you're only about 2 weeks in, can read and comprehend that code that I wrote. And I think we get that readability because we're using our language mechanics and our language syntax to read that, and also the way Go has been put together, right? So from my perspective, I mean, this is code that is highly readable, highly comprehensible by a lot of almost all Go developers, and I would even argue maybe developers not even are just seeing Go for the first time. But here we are, we've got this great piece of code. But if I wanted to start to print a collection of strings at this point, because the type information is changing on the parameter, I've got to go ahead and write another function. And we can all see that the 5 lines of code for the print strings function is really identical to the 5 lines of code in the print numbers. The only difference is we're changing the variable names, the identifiers, to make it more sense in terms of the data that we're working with. But the mechanics and the language syntax is really the same. So let's run through maybe a thought experiment for a second, because when I see this and now I think, well, let's write a function now that works with floats, I can make the argument that because this code is so readable and comprehensible, maybe it's not a bad idea to copy and paste and write a print floats. But I think part of our humanity here, right? Like what we've been taught is, Phil, that's going to be a lot of code to manage. And then the question becomes, well, is there a way to consolidate this code to make it maybe easier to manage, but still maintain some readability and comprehension? When we have that kind of thought experiment, we think about it, and we're talking about the current compiler we're using today, I come up with this. And here on line 35, what you see is a function called print, and I've called it print assert. Now, the idea here is that we're going to be consolidating those functions that we wrote into a single function to help with that maintenance here, right? I'm trying to still maintain readability and comprehension. But right away, you see the use of the empty interface, because if we're going to consolidate all of this, we need a way to be able to accept a value regardless of what it is, right? And the interface is a way of defining a constraint on behavior, and the interface itself says it doesn't have to have any behavior. And so this is the mechanic we have today in the language to accept data of any type. Now, as soon as we abstract this data inside the interface, we're really now blind. We don't really know what's in there, right? And so now on line 37, we have the ability to perform that type assertion. In fact, because we're on the switch, we can do this generic type assertion, right? And what we're saying here is let's type assert on the concrete data stored inside of V. And then we have our case statement. If it's a slice of int, excellent, let's execute this for range. If it's a slice of string, let's execute this for range. We're still using our language mechanics. We're still using our language syntax. We're using our variable names that make sense for the data we're working with. However, there's one slight problem with this consolidation. That's all it is. If I now want to work with a slice of floating point numbers, I've got more coding to do. And so I think we've solved maybe a maintenance issue here. We're leveraging a language syntax and semantics, but this really isn't a generic function. This won't work for all slices that we can potentially pass in. And so now we move that thought experiment a little bit farther, and we say, well, is there a way in Go 115 right now today to actually write a generic function like print that could print ints, slices of strings, and slices of floats, slices of user? And the answer actually is yeah. We can do it. we could go into the standard library and use the reflect package. The reflect package does give us the ability to write generic code today. Let's look at the implementation of this function. We're going to leverage the empty interface again because we can't have a restriction on passing the data regardless of that type. But now we have to the problem is we got to walk away from our language mechanics and our language syntax and now start working with an API. And anytime we're working with reflect, it all starts with this value of function. So we can get this reflect value that lets us do that, reflect, inspect the concrete data stored inside of V. Now, the very first thing we have to do here is validate that we were even given a slice at all, because the empty interface isn't restricting somebody from passing anything in. And then we got to return. Now, this potentially changes the semantics of the function because I could pass something and not see anything in terms of output. But again, you know, the point here is that we are able to write this generic function, though the semantics are changing. Now, I can't use my for range here, right? I'm going to iterate a variable named I, but through the method set of that reflection package, I can at least index and do my linear traversal over I, and then this interface method here gives me access to the value, and then I'm able to print everything out. And this code here doesn't care whether it's a slice of int, a slice of string, a slice of float, a slice of user. It only really cares that it's a slice. Pretty cool. And so here I actually wrote a generic function using the reflect package. Now, if we look at this a little closer, I had to use 8 lines of code instead of 5. And I really can't make the argument anymore that all Go developers of almost all levels can look at this code quickly and read it and comprehend it. Because again, we walked away from our language mechanics and syntax and went to a package API. Now, what's interesting is in all of these examples, I'm using the print function, which technically also is a generic function in Go, because print is also using the reflect package underneath to be able to display a value of any given type. And so we see reflect kind of all over this. But if our goal is to always be able to write code that can be read and comprehended by the maximum number of developers that we can, then it begs the question, is there value in adding generics into the language where such we could write functions that are generic like this, but get back to our traditional language syntax and mechanics where I'm making an argument that more people can read and comprehend that code? I personally think there is. And so let's now look at what, based on the draft, what a generic function could look like to write this code without having to use the reflect API. Now, on line 80, this is our generic function based on the new syntax. And I really want to spend a little time here breaking this down. But before I do want you to focus on those 5 lines of code. And what I want you to recognize is that these 5 lines of code are really the same 5 lines of code I started with when we were printing those integers and strings. Because this function gets to get back to the roots of the idea that we're working with that concrete data. And therefore, we can work with our language mechanics and our semantics. We've got our label, we've got our for range, we're using our print, and we do the carriage return line feed. And now we're back here saying, I think, that we can have more developers read and comprehend this code than we had before. Now, I want to break down the new syntax, and I want to explain why we need new syntax. And so what I'm going to do is remove this for a second. And you're going to see me do this throughout the talk. I'm going to remove it, we're going to put it back in, and we're going to talk about it. Now, because we can do this with our brains right now, if you look on line 80, I think you get a general idea of what I want to say. What I'm trying to tell the compiler is that I would like this print function to work with a slice of some type T. Listen to what I'm saying, some type T. That's the idea, where T can be filled in later, where T can be determined at compile time, at the time you hit the button, not before. But the problem is this syntax right now is what we have today. This syntax assumes that some type named T is going to be declared somewhere in some source code file before I hit the build button. And that's really the exact opposite of what we want. I don't want this T to have to be defined. I want the T to be defined at compile time, right? And so what we need to do is we need a new syntax to be able to tell the compiler that don't go looking for a declaration of some type T, because it ain't gonna exist. If you go looking for it, you ain't gonna find it. What we need to do is somehow tell the compiler this, that T is gonna be a generic type to be determined at compile time, at the time we hit the build button. So what new syntax do we have right now in the draft to give that information to the compiler? Well, currently, this is the syntax that we're working with. It's a set of square brackets that are attached to, in this particular case, the name of the function. And what these square brackets do is list out the set of type identifiers that will be recognized as generic type identifiers to be determined at compile time. It's these square brackets that give the compiler that information so it doesn't go off and start looking for it somewhere else. Now, in the latest version of the draft, which changed, I think it was last week or earlier this week, I don't remember anymore, they made a decision that all type identifiers in this type list need to have associated with them also a constraint. Now, the very last two examples in this talk will be very much focused on constraints. So I don't want to get down there right now, but they did add this pre-declared identifier named any to represent that T can be anything. In other words, there is no constraint. It's a constraint that applies no constraint. And it probably ends up being implemented as an alias somehow of the empty interface. So any is really associated with the idea that there is no constraint on this. But I just want you to see for now, you're going to see me typing any in here to represent the idea that T can be any type that we want it to be. There is no constraint on what T can be. And I promise the last two examples, we'll explore that a little bit more. Okay, great. So now we understand here that we needed a syntax to inform the compiler that this identifier T will be a generic type to be determined at compile time. And the current syntax choice for that is to add this type list with a constraint to represent those generic types. There we are. And I want you to also appreciate that the idea of this generic type T is to be a concrete type. And so we're really writing a function that will accept data based on what it is, an int, a string, a user. And that's what is allowing us to use our language mechanics and our semantics in the implementation, in this case, of the print function. Okay, brilliant. So we've kind of got this syntax now in place. It's just these square brackets here attached to the name of the function to represent the generic type. And now we are saying that print can accept a slice of some type T to be determined at compile time. Great, let's run this code, get a general sense of how this works. So on line 91, I've constructed a slice of integers. I've constructed a slice of strings on line 97. And one of the things I really wanted to do in these early examples is be able to pass the same exact data to all the different functions that we're writing. And so you can see here, I can pass that slice to those four functions. I can pass that slice of strings to the other. Now, let's go ahead and transpile and run this code, and then we'll explore a little bit more about this code as well. So I'm going to come into my terminal window here, and we're going to go into the O1. And I want you to notice here that we have a file with a go-to extension. All right. Now, the transpiling tool is expecting that we have this go-to extension, which again will transpile it into Go code, and then we'll be able to build it. And to do that here with the current version of Go that I have, we're going to access the Go tooling through the Go tool sequence of commands. And then from there, I can say build, I can say run, and I can say run this Go file. And now what it just did is transpiled it, built it, ran it, and we see the output. It's the same thing that the Go playground would do. I'm doing it here on my local machine. And the big win here, right? The big win here is that I could now just say take line 91, maybe we'll call this floats. We'll turn this into a float 64. we'll just make sure that these are floating point numbers, whatever they are, it's not important. And like I said, I really do have two generic versions of print right now, don't I? I have print reflect, and I have our print function itself. I don't have any other way to print these floats because we didn't implement them in the assert, and I didn't write a print float, but I do have this. And just by doing that alone, we get to see some floating point number show up on the screen. It's beautiful. Now, let's talk about one more important piece here. And that is the idea that in this case, the tooling, but eventually the compiler, will have capabilities of being able to infer what type T is. And that's an important aspect, I think, of the implementation. Because we really want to use these generic functions no differently, or call them no differently than we're calling any other function. And in this particular case, life is good because when we pass this slice of int into this parameter slice, the compiler knows, okay, they're passing a slice in int, so T must be an int. And what we're seeing here is the tooling be able to infer that T must be an int based on the data that we're passing in. It can infer that it's a float. It can infer that it's a string. Now, there may be times where the compiler is not going to be able to infer the type. Maybe you're not using T in the parameter list. Maybe T is just being used somehow directly in the implementation. And so you need a way of also being able to be explicit and tell the compiler what T is going to be. We would prefer that the compiler can infer that information. It'll make the syntax, like on line 95, look more like what we're doing in any function call, but there are times where we might have to be explicit. And so just like this is defining a set of input parameters, this syntax is also defining a set of parameters as well, T being that generic type, but we can also pass in explicitly what T is going to be and tell the compiler, don't worry about spending time inferring this. I'm letting you know that T is going to be an int. I'm letting you know that T is going to be a float 64. And you can see this still works. And so we're also capable, and I would say we would only want to do this when we have to. We're also capable of being able to pass in the type information as a parameter using that same square bracket syntax. But when the compiler can infer the type, like it can in these cases, because the T, generic type T, is being used on the first input argument, and the compiler can figure that out. It's really nice. Okay, so we just sum up what we've seen so far. We've seen the use of a generic function to be able to work with a concrete type, but a concrete type of, in this case, some type T to be determined at compile time. But because T will be this concrete type, we're able to write code using our traditional language syntax and mechanics, which again, I argue is more readable and comprehensible by more Go developers. We've also seen that when we're calling these functions here, that the compiler can infer what type T is because of the, because in this particular case, it's part of that data input. And then when the compiler can infer the type, we can pass it in. Okay, brilliant. Now, this is nice. We've got this generic function. We've looked at a function here. But if we're really writing real world applications like we do each and every day, well, data is important. The ability to define a user-defined type is really, really important. And we're going to want to apply generics to those user-defined types as well. And there's really two ways to define a user-defined type. You can define a type based on an underlying type, and then we can define a type based on that keyword struct. And so we need to kind of explore where generics fit in for both user-defined types using an underlying and a struct. So we're going to start with the underlying type here. And I want to kind of go through the same sort of progression because I think it really helps to solidify the new syntax and the benefits we're getting on that readability and comprehension. So if you look on line 16, I'm defining a type named vector int, which is based on an underlying type, which is a slice of int. And on line 25, vector string is that slice of string. Okay, great. Now, to make this example more interesting, I've added a method named last to both types. And the idea of last is to return the last value, the value at the highest index position in the vector. And so when we look at the implementation of last for vector int, we first check to see if that slice is empty, because if it is, we'll return an error and the 0 value for an int in that return position. But if it's not empty, then we can return the value at the highest index position, and then we return the 0 value for an error. And if you look at the code over here on lines 28 through 31, it is again the same code, the same language mechanics, the same syntax. The only real difference is that we're working with a string, and that the 0 value for a string is an empty string. And you can already imagine if I now wanted to do this with a float, here we are again, copying this code, changing out variable names, changing out type. But there is some advantage to these vectors, and that is that when I call last against a vector string, I know I got a string. When I call last against a vector int, I know I got an int. We know what data we're working with, we know what data is coming out of this API, and that makes the usability of this vector really nice. Because if we go back down through our thought experiment, we could ask ourselves, well, is there a way of writing a vector in a generic way today, let's say in Go 115? And the answer is yes. We could define the vector using the empty interface. And if you look at the implementation of last, it is again the same lines of code. We have to check for empty, and if it is, we return the 0 value, which is a 0 value of an empty interface, which is nil, or the last value. But if you think about it, this vector has a different semantic than the other two. And that is that this vector can store data of any type. And the reality is that when I call last, I really don't know what concrete piece of data came out of the vector. I really don't. I'm going to have to go back and do type assertions. I'm going to have to do an extra level of check. And that, I think, could hurt our usability. And so what I really want is a vector that has those semantics of vector int and vector string, but to be able to define what that vector's type is at the time that we compile and build this program. Here it is, generics again. So how can we do that with the new syntax? And like I said, I'm going to remove the new syntax and then bring it back in. So if you look on line 57, what am I doing? We on the surface know what I'm trying to do. You know what I'm trying to say. I'm trying to say, let's define a type named vector whose underlying type is a slice of some type t. Some type t to be determined at compile time. And once again, as soon as I say some type t to be determined at compile time, what does that mean? It means now I've got to apply the new syntax, because it's the only way to tell the compiler that t is a generic type. Don't expect me to define t somewhere. It's not going to happen. So every time I think of that type identifier being a generic type identifier, and then I know I've got to apply the new syntax to tell the compiler t is a type to be determined at compile time. Great. Now, when we go ahead and implement last, what's interesting here is that we want to return a value of some type t. And so we can apply that t now to the return, but I want you to look at the receiver, because I can't define the receiver like this. It doesn't really apply, because vector in and of itself doesn't mean anything unless we know what type we're applying to that vector. And so in this particular case, since we still need to determine a compile time, we use this same syntax here to say that this is a method for a vector of some type t, returning that same value of type t. There we are. Now, if you look on line 61, we're able to use our same language mechanics. We check if it's empty, we return an error, or we can return the last value in the highest indexed value in the vector and a nil. And what's beautiful here is that when we run this for what we are going to define for t, we know what we're getting back. We've got all the same language mechanics and syntax we had for vector int and vector string, but in a generic way. Now, there's another thing here that I just bypassed, and we're going to talk about it, and that's 0 value, because we have an interesting mechanic here. I want to return the 0 value for type t when there's an error. I love this idiom in Go. I love this guideline. I think it really helps with readability on the return. So you always use the literal value or literal construction of the 0 value for those arguments that really we're not necessarily passing out. And so we need to be able to construct a value of type T set to its 0 value. Now that gets interesting because you need a syntax that works for all types, regardless of what T is. A lot of people, when they see this, the first question they ask me is, well, Bill, can't we just do this? Can't we use empty literal construction of T on the return? Because, you know, we do that when we've got a user. So why can't we do that with T? The reason we can't do this syntax is because even though this works for user, it doesn't work for int, doesn't work for all types that T can be. And so that syntax isn't really valid. We need a syntax that works regardless of what T is. And right now in the language, we've got two choices here. Now, the first choice that I'm showing you is the one that I prefer, at least right now. And you see that on line 60. You see me using the keyword var, variable name and T. This is, I'm going to call universal. We can construct a value of any type using that syntax set to its 0 value. There it is. T could be an int, T could be a user, T can be anything. We're going to get 0 value construction. And so now this will allow us to construct and then return a 0 value. And I think the readability of that 0 variable works really nice. Now there is another way to construct a value of some type T regardless of what T is. And that is with the use of the built-in function new. New will construct a value of any given type to its 0 value state. The problem here is that new returns a pointer. And so we need to apply the dereferencing of that pointer to make the syntax work. Now, I've met people who prefer what I'm doing on line 62 over the use of the 0 variable. I mean, this is a guideline and an idiom the community will have to come together on at some point. But if we're really focused on having the majority of people be able to read and comprehend code, I'm going to make the argument here that this 0 variable is going to extend itself better across more developers than this syntax that looks, to me, kind of foreign and scary. And so you're going to see me doing these types of things right now, but both syntaxes will work because both syntaxes do allow us to construct a value of some type T regardless of what T is to its 0 value state. Okay, so I've shown you that here. Now let's see a little bit of this code running. So really quickly here. You see me constructing our vector int. You see me constructing a vector string. The big thing here is that when I call last, we know we're getting back an int. We know we're getting back a string. And so since I know it's an int, I can even apply logic to the last value. I can check if it's a negative number. Here I can check if it's a valid string. The usability goes along with the vector because the type information is known about what the vector stores. But I wanted to share with you that when we use vector interface, the semantics changed. Look, I'm blending data into this vector, int, string, float. Now, when I call last and it returns, I'm getting an empty interface and I have 0 clue at this point what concrete data is stored inside of ITF. And so here we are doing type assertions again, because if I still want to apply this special case logic to the data, then without the type assertion, I can't. And this is what I'm talking about in terms of the usability of this vector over the other. But when it comes to our generics here, now we get to specify. Now, what I'm going to do is a couple things up here so we can get a better understanding of what's happening. Now, think about this for a second. I want to construct a vector to its 0 value state. Well, that's not enough syntax, right? Because we define vector as a generic type, and we need to know what that type T is going to be at compile time. And so that square bracket syntax again becomes important, because in this particular case, the compiler cannot infer the type. There's just nothing for the compiler to hang its hat on to do that inference. So in this case, we have to be explicit with the 0 value construction and tell the compiler, I want V to be a vector whose underlying type is an int. Oh no, maybe a float. Oh no, maybe a string. Here, you can see a case where we have to be explicit and use this syntax. Okay, and if you look at the receiver, I mean, you see that that same syntax is here, right? It's almost like that construction syntax, a vector of some type T, some type T. There it is. Now, when it comes to constructing this vector, where we're going to use that literal construction, right? You're seeing me, both on line 110 and 118, still explicitly pass the type information for T. You might be saying, Bill, can't the compiler infer that the type T is a string because of the initialization syntax here? And you know what the answer to that is? Yes, absolutely it can. But remember when I started this talk and I said that the draft isn't 100% implemented by the Go tooling just yet? Yeah, here's a piece where this absolutely can be inferred. It just hasn't been implemented yet. Ideally, when this actually hits in a real release, you'll be able to do that. You won't have to pass in string explicitly on the construction. But that syntax won't work today in the current tooling because it's not implemented. That's all. I just wanted to share that with you. And that's why what you're seeing here on line 108 and on line 116 is me explicitly passing in. But what's beautiful here is when I call last, I know I have an integer, boom. When I call last here, I know I have a string, and then I can do that same sort of validation without the type assertion. Now, if I go ahead and run this code here, we can see here that I've got no compiler errors. And if you really focus down here, you can see here that I was working my vector int, checking negative numbers, working with string non-valid. And again, what is the beautiful part of all of this, right? The beautiful part is if I now decide that I want to work on a float, right? I don't have any more implementation details that I have to deal with. All I get to do is construct now a vector of that float type, right? And I can just go right here and play with some variable names here, float, and I can even use the right verb for the float because I now know I'm working with that float, right? And I can come back here and we can run this. You can see I have a compiler error on 117 because I'm not perfect because I need a short variable declaration operator. And I beat Kevin to that, so I feel good. And there we are, all right? Didn't have any extra implementation. I just told the compiler that now I want a vector of that float 64, and now I get to work with the float. Beautiful. And again, we're back. I think the beautiful thing here is we're back. We're back to writing code as if T is an actual concrete type. And I think that's where that readability and comprehension comes in. We get to walk away from the type assertions. We get to walk away from the reflect package, and we get to have code that is more language mechanics, syntax based, not API based. Now, I'm going to say this before I move on. I love the reflect package. This isn't me saying, let's get rid of it, because the reflect package is an amazing package. We can do data validation with it. We do marshalling and unmarshalling with it. This isn't about getting rid of it. It's about cases where our comprehension and readability can be improved by using language mechanics and syntax as opposed to using the API. And we have to make that engineering decision. Okay, it's 8:21. I'm in good shape. I'm good shape. 21 after the hour. Now, I've shown you the underlying type here. Now let's look at the struct type, because the reality is we probably use struct types a lot more than these underlying types. And what I wanted to do for the struct type was focus on, I think, a big benefit of generics, which are these, what we call these container types, where these data structures, linked lists, trees, hash maps, all this stuff, right? And I'm going to have a basic implementation of a linked list here to give you an idea of things that could be implemented now with the current support that we're looking at in the draft for this first release. Now, once again, I'm going to get rid of some syntax here, and I'm going to talk about it. If we're going to implement a linked list, then we're going to have this node, right? And the idea of the linked list is that we use pointers to bind all these nodes together into a data structure. And today, if we wanted to write a linked list that was, we would have to specify specifically what data we want, or we would be back to that empty interface, right? And then we're back to the type assertions again. And so ideally, what we would love to be able to do, because the majority of the code we're going to write for this linked list isn't based on the data, it's based on the mechanics of linking this all together, is I'd love to have a node that said that the data will be of some type T to be determined at compile time. Every time I say some type T, what does that mean? It means I'm coming back and doing this to tell the compiler that T is a generic type. There we are. Now our next and previous pointers, they have to point to nodes, but not just any node, nodes of the same type T. And so you see that construction kind of syntax again, don't you? We saw that on the receiver. We see that on the construction. Node by itself has no meaning. Node must be told what type of node this is. In this case, it's going to be of that same generic type T. Now the list has a first and last pointer. So once again, of some type T. So we apply our T any again, because T can be anything. And we see the same for first and last as we saw for next and previous. Now, I implemented an add method here. And once again, you see the same receiver, a list of some type T, that we're using pointer semantics. It returns a node of some type T, using pointer semantics, and accepts a value of some type T. There it is. And then on line 26, you see construction syntax, literal construction, where we're constructing a node of that same type T that we pass the data in. And then there it is, we can assign the data. So it's all about telling the compiler some type T, some type T, some type T, there it is. And the majority of the code that I'm gonna have to write after that is all of this wiring up, right? This is the same regardless of what T is. And so you can see here kind of the beginnings of how we could start to define these kind of container types. Here's a linked list that could be based on some type T, but remember T at the end of the day ends up being this concrete type. And that again always gets us back to our language mechanics and syntax. Now, instead of using a scalar type here, I'm defining an actual struct type here called user. And then if you see on line 53 and 59, I'm constructing a list set to its 0 value using user, a value of type user, which means add accepts values of type user, and these data fields are values of type user. But I can also construct my list set to its 0 value based on a pointer of type user, which means add is now working with pointers of type user. Look at the address ampersand construction, and data are going to be pointers of type user. And we can see that in the output, because fortunately print will not apply the ampersand unless that data type is pointer. And so you can see here, we're working with values of type user, working with pointers of type user. Now I just want to show you something from a semantics perspective that I think is important. I could do the following if I really wanted to. I could enforce that regardless of what T is, I'm going to use pointer semantics to store it, and I'm going to use pointer semantics to receive it. I could do that. We wouldn't apply that here because this is a type identifier, but I can apply it here to the field, and I can apply it to the parameter. Now, what happens if I do that? Is there any sort of problems and or maybe readability issues? Let me comment that out for a second, and we'll just focus here. Because I want you to know that I'm passing user a value of type user, right, for T. What happens now when I compile this? Look at what the compiler tells us. It says, Bill, you can't call that add function because we're now expecting you to pass in pointers of type user. Well, that's fair. I mean, if you look at add, I'm saying pointer of type user. So I've got to go back now and do this sort of construction. Okay, that's fair. That works. What's happening here then? Now I'm passing a pointer of type user for T. What's the compiler message we get now? A pointer to a pointer of type user. Yeah, of course, because think about it. I'm basically telling the compiler that T is a pointer to a pointer, or a pointer of type user, a pointer of type user. See the substitution that now takes place. Now we've got this double indirection that's going on. So my point for showing you this is the following. I think that there's some really nice value in not hard coding into the fields and the parameters that kind of pointer semantic, unless you really have an implementation that just can't be based on the value semantics. And the reason I think is also for the readability and comprehension, because on the construction of list, if I'm saying T is a user, then we know everything that we apply is also based on user. If I say a pointer, then everything's pointer. In other words, I am allowing the developer or the user to dictate the semantic that they need for their own data. I'm not enforcing it on them. They get to choose. So I like this idea of when it's reasonable and practical to do so, that we allow the user to apply the data semantic that they want. But if you do have a reason to do this, right, where we put the star there, just be aware that there could be like a little bit of confusion on the form of the construction and then everything else. Okay, great. So we've now seen how we can work generics into using our struct types, where these fields are going to be based on some type T to be determined at compile time. Okay, brilliant. What time is it? It's 8:30. Oh, life is good, because we now have to have another conversation. And that conversation comes back to constraint. Now, when I showed you that original generic function, we talked about the idea that that function can work with any type T. There was no restriction on that code to what type T could be. And that's great, but the reality is that we're going to have functions that at some point just can't be any type T. That what T can be is going to have to be restricted. And that's when we start talking about constraint. What is the constraint on what T, in this case, can be? Now, there's really two types of constraints. And I want to talk about the first one, which is behavioral constraint, because that's something we have today in the language. The idea that we want to constrain things based on whether or not that data can exhibit a certain behavior. So let's kind of focus on behavioral constraint first. Now, to do that, you're going to see here on line 13 and 22, I'm defining some struct types. Line 13 is a user, line 22 is a customer. And then on line 18 and 27, I implement a method named string that returns a string. And the idea of the implementation of this method is to be able to stringify a user and stringify a customer. Now I'm hard coding the JSON here. There it is. I mean, I'm just doing it by hand. That's fair. But if I had another entity type, whatever that could be, and I implemented a string method again, and I could stringify that. So here it is. I've got entity types. They're struct-based. I've got methods that can stringify each particular type. And then the idea is, well, what if I have a collection of users or a collection of customers? I'd love to be able to iterate over that collection of users and stringify them all and return that back in a collection of string. So look at the 5 lines of code to do that, right? I can call make to construct the slice of the proper capacity based on the length of that slice user. Then I can use my for range mechanics to do that linear traversal. And then I can use append to apply the string that is produced by the string method. And the compiler knows this user has a string method. You saw it too. And now I can stringify all of the users into a single string collection. And I can use append. And again, these 5 lines of code are the same 5 lines of code here. The only thing that's changing is the type information and some variables. Now, I do want to take a small sidetrack here, because one of the reasons that we're able to write this code as similar as it is because of append. Go has a set of built-in functions, right? Append, copy, make, new, close, delete, len, cap, sure I'm missing one. But we have all of these built-in functions. And when you think about the built-in functions in Go, I think you start to realize, I do, that all of these built-in functions are generic functions. Think about it. Look at append. Append can take a slice of any type and a value of that same type and perform the operation. New can construct a value of any type T. These are generic functions. like we can almost make the argument that Go already has generics as it relates to the reflect package and the built-in functions. But let's be fair, we don't get to use the same mechanics to write generic functions as the language team does as it relates to those built-in, right? Those mechanics are not extended to us. And so it's easy for me or anyone to say Go already has generics, but it's also not necessarily fair because we can't write functions like append today. And we already talked about that when we're using the reflect package API, we're walking away from our language mechanics and syntax. We're working with an API. But just want you to realize that a generic function is really also helping us keep this code very, very similar. Okay, we go back to the thought experiment, and we could consolidate all that again, right? We saw this code already. I'm not going to break it down. You see it, empty interface, type assertions, you get it. But this only works with users and customers again. Can we do this? Can we write this function in a generic way using the reflect package? Guess what? I absolutely can. Now, there's 13 lines of code here instead of the other 5. There's a lot more API calls. This doesn't really look and feel like Go as related to the other. This is all a matter of APIs. But if I broke this down, empty interface to accept any type of data, reflect.value, is it a slice? If it's not, return nil. Again, we could potentially pass data here and not see anything. Okay, I have access to a method named len to be able to get the length. We use our for loop again like we did before. This is cool. For every value stored inside of that slice, I can ask the reflect package if it exhibits that string method behavior. And if it doesn't, well, I return nil, but if it does, I make the call. So I have access to the string method here to do the actual stringification. And then I can apply my append. Now, this code isn't nearly as readable as the other code, and there are some semantic issues depending on what is passed, right? And it's all being done at runtime, not at compile time. But heck, I got a generic function, here it is, and it will work for any slice that contains data that can string. But again, we're doing everything at runtime. Okay, let's take a look at this as it relates to the new generics syntax. And once again, I'm going to get rid of that so we can break it down. And again, look at the code I'm writing here. It's the same code we wrote for user and customer, right? And again, I'm trying to say, I will accept a slice of some type T to be determined at compile time, a generic type T, which means that I can get its length using the built-in function len. It means I can for range over it. I can use append. There's the string method, that's interesting, and then the return. So if I do this, like we've been doing, if I right now just say, fine, we know T is a generic type, let's add the brackets, let's add T, and let's tell the compiler that T can be anything. What happens right now at compile time? Let's take a look. It didn't compile. What is the compiler telling us about line 114? It's saying, Bill, we got a problem here because you're calling a method named string, and you're not really telling me that T must be able to, or at least values of type T must have a constraint that they can call, that they can string. You see what's happening. We're not giving the compiler enough information to be able to, at compile time, make sure that T can do we can call that method. Now, if you think about it, what the compiler needs is a behavioral constraint against T for this method set or this method of behavior. And we kind of do this already today, right? I mean, look, I can write a function named Bill that accepts a value of type user. What is this function saying? It's saying that I will accept just values of type user. It's asking for data based on what it is, a user. But I could today write what I'm going to call a traditional polymorphic function in Go, where we don't use the concrete type, we use an interface type. And this interface type exists already in the fun package. It's called stringer. And this interface defines a single method of behavior called string that returns a string. You see, on line 115, this is our traditional polymorphic function. And what it's saying is, I will accept any piece of concrete data as long as it knows how to string. In other words, it's asking for data not based on what it is, but based on what it can do. We're leveraging what it can do as the constraint. And we really have the same situation here, except it's not necessarily, except here, it's based on this type T constraint, right? And here I'm saying data. We have to be able to apply a constraint to T so we can make sure that we can only use types for T where their data values that support this method set. But here's the interesting thing about a generic function, right? It's not a traditional polymorphic function in the sense that it's not ever asking for data based on what it can do. It's always asking for data based on what it is. Our generic functions are not this. They're this, where user gets substituted in. So it's super interesting here because our generic functions are really concrete functions, but we have this behavioral constraint. Now, the idea in the draft right now is to reuse the interface to apply this behavioral constraint to T, just like we were applying it to the data that we could pass in our traditional polymorphic functions. And so if I replace any with stringer, now this gives the compiler the information it needs, telling the compiler, look, T can't be anything. It can only be a type whose value implements that string method that you're seeing on line 114. And it's kind of like the reverse of our traditional polymorphic functions because it's still asking for data based on what it is, but then we're applying a constraint on what that is can be. And now if I do this and we run it, it builds and it runs and we see this stringification of users and customers. Pretty cool. And so we have that. Okay, so the reuse of the interface to apply those behavioral constraints for type T when there is a method that we're saying needs to be called for values of type T. There we are. Now, I'm not going to go any farther in here. You can imagine I can write new types and do all of that. And this is cool. But I want to get now to the last example, because since our generic functions are really concrete functions, because our generic functions are asking for data based on what it is, some type T to be determined at compile time, there's actually another constraint that exists that really doesn't apply to our traditional polymorphic functions today. And because of this, there is another piece of new syntax that we now have to introduce into the language to support it. And this type of constraint is what I call operational constraint. You could potentially consider it behavioral, but I'm not, because it's not based on methods like you see on line 114. It's really going to be based around operations like adding, subtracting, comparing. Think about it. If I'm performing an addition operation, well, that has to limit what types I can use. If I can't add two concrete types, I can't add two struct types together, and we don't have operator overloading in Go, and don't hold your breath for it because it ain't coming anytime soon. Okay, even Kevin's shaking his head, right? And if I'm using subtraction, well, guess what? You can't even use a string because you can't subtract two strings. So you see that we have a type of constraint that doesn't really apply to our traditional polymorphic functions, will apply to our generic functions, and we have to handle this. So let's take a look at the current draft syntax for handling this type of constraint. And I really want you to do your best right now to focus on line 16. Look at what I'm trying to do on line 16. I'm trying to say, let's accept a value of some type T and a second value of some type T. Let's add those two together and return a third value of some type T. Again, we know that T is a generic type to be determined at compile time. So I might really quickly do this. But it can't be anything. T can only be of a type whose data can be applied to that operation of add. And our interfaces today are based on method sets. They're based on methods. That's not a method. So we need a way to apply a constraint to T where we can have at compile time a guarantee that whatever type T is, it will work within the scope of this operation. Now, the draft is currently experimenting with this syntax right here. And the idea is to take our interface, which we use today for constraint, and reuse it to apply this form of constraint, which is a type constraint. And essentially what we're saying on line 13 is that the add-only interface can be used to constrain T in the add function to just those types alone. Remember, this is a generic function where we're still talking about the data, what it is. But now what we've done is we've given it a list of all potential types that T can be, and it can only be in this list. Now, just to be fair here as well, if I did define a type named Bill, whose underlying type was a string, Bill would be compliant with this type list. Underlying types can be matched here. You wouldn't have to worry about doing this. The underlying type would be matched. That's good. But you can think about how restrictive this is for our user-defined types, because if we have to hard code this type list, then it could only be based on the known types we have within the scope of this package, let's say. And it really can't be extended beyond the developer developing this package. There's some limitation there, isn't there? Outside of the underlying types. There it is. And so now what this is doing is letting us apply this sort of constraint to make sure that these types are just types that can work with this operation. Now I want to say a couple things to you here. The language team working on generics is not happy with this syntax. They really aren't. They've expressed that to me. Because as soon as we add a type list inside of this interface, it can no longer be used with a traditional polymorphic function. In other words, you're not going to do this. This absolutely doesn't even make sense, because remember, our traditional polymorphic functions are not about asking for data based on what it is. It's asking for data based on what it can do. This interface is describing nothing about do. It's just limiting as is. And so this syntax doesn't work. It's not going to work. It doesn't apply. It doesn't make sense. And the language team's really not happy with that, because we don't do these types of things in Go, at least not today. And so they're really looking for thoughts and ideas about this specifically, and if there's better ways to do it. Now, I will tell you this. Some of the things that I've seen on the mailing list, okay? Some of the things I've seen on the mailing list would be just let people apply it maybe here. Okay, potential idea. Another idea is, why don't we just maybe put the list of operators that we're going to support and then let the compiler figure it out. I'm just throwing ideas out that I've kind of seen on the mailing list. And Ian has reviewed and discussed all of those, all right? So this is something here that there is absolute work that needs to be done. Maybe it's really one of the higher priorities of work that we have to think about in terms of syntax. I'm going to get back to this. But I also want to share with you the idea that they have with pre-declared type constraints. And this is one they've provided called comparable. And there's others thinking that maybe there's a standard library package called comparable with a bunch of interfaces maybe predefined as well. But what's nice about comparable or the pre-declared type constraints is, in this particular case, you don't have to worry about defining these interfaces, right? You'll get them for free. And in this particular case, we need a constraint. In fact, that's old syntax now that I see it. I don't know why I didn't fix that. We need that comparable constraint because we're doing that there. All right. Let me show you one more thing that we can discuss. And I've got 3 minutes. It's going to go a little over. But there's some interesting things here that will kind of really kind of get us to that like 80, 85% that I wanted to share with you. And let's focus on line 75 for a second again. So what am I trying to do with the match function? I'm trying to take a slice of some type t and a value of that same type t. And then I'm going to range over that slice of type t. And for every value in the slice, I'm going to call match behavior against it, passing this value of some type t into it. So what do we already learn tonight? Well, since t is a generic type, we know we need this syntax. Except t can't be anything because on line 77, I'm calling match. Guess what we need? We need an interface. We need maybe the matcher interface. Now, what should the matcher interface do? I'm going to get rid of this for a second. The matcher interface needs to define this match behavior. But look at what's interesting here. You see, this match behavior also has to be based on generic type t because we're passing find. So when I declare the matcher interface, I have to declare it with a generic type t that can be anything because that's the parameter type t that needs to be passed to match. And so it also shows you how you could define behaviors that both accept and return, right? Values of a generic type. And you can see kind of an implementation of that right here in 76. So really cool there. Now, I got rid of this because it's the last conversation I want to have with you. The current draft says that this is legal syntax, that you can define an interface that has both behavioral constraint and type constraint. Now, this really doesn't necessarily make sense for this match function because we're not doing anything operationally that would require the constraint. I mean, if I decided to write code like this, well, that's a different story, right? There, that would work. I can compare, well, 2 persons or 2 foods. I can do that, right? So, but I'm not doing that. So I really don't need this syntax. Now, I have struggled to find a practical need for this sort of syntax. I haven't been able to find one. Doesn't mean there doesn't one exist, but I haven't been able to find one. And a part of me thinks that maybe at the end of the day, we identify that this isn't even necessary. And if it isn't, this could potentially help us solve the problem that I started this exercise with, which is putting those type lists in interfaces anyway and causing them now to not necessarily work everywhere. But I did give a talk about a month ago, and somebody came up with something really interesting here that I love sharing in this talk. They said that they were building a very large code base that had a lot of regulatory compliance that they had to build into it. And the developer looked at this and they said, you know, Bill, what would be really cool here is that if I had a function that I really wanted to make sure wasn't executed against any sort of data, but very specific pieces of data in the program because of compliance and things like that, this type list would kind of give me that compiler level protection. Because in this particular case, it's not enough that you know how to match. We can still only pass person and food in here. And that developer thought, wow, that may, you know, this type of functionality potentially could have helped me in that other code base. Because even if a developer came in and added the next type, we could have seen that. That's much easier in a code review. And then we could have said, whoa, I appreciate that you implemented match, but we don't want that data flowing through here. That's a no-no. So I don't know, it's interesting, right? When you think about maybe in a regulatory environment, maybe in something you're doing, to be able to have that check and balance on what data is actually flowing through there. I don't know, I'm throwing it out there as kind of, again, a thought experiment, but I haven't really been able to find a practical example where we're leveraging both behavior and then sort of operational constraint where we would necessarily need that. Okay, brilliant. So I did really well tonight with you. It is 50 after the hour. And so what I'm gonna do is stop sharing. Yeah, this is cool. I really love all of the conversations that you're having in chat. That is brilliant. Now, Heather and or Warren, I'm absolutely here available, and I'd love to get questions and or comments, but we are 34 people strong. So walking through 34 people will take a long time. So I'm not sure how you would like to give those who want to speak an opportunity, but I would love to hear thoughts and opinions, even if you don't have questions.
Yeah, so I have a suggestion. If people can see the raise hand feature on Zoom, like if you click the participants list, and if you'll see there's like a raise hand, if you'll have any questions, y'all can click that, and it should show up in the order of who raised the hand first, and then I can call on that person, and y'all can go ahead and ask that question. I think that's one way I've seen
But
us do it.
even if you don't have a question, I don't have a problem if you want to take a minute or two to express some thoughts or opinions or share. Like that's what this is for too, okay? So, but just a minute, if it's not a question and you want to express some thoughts on just a minute or two, just respect everybody's time. That's all I ask. Kevin, of course. So Kevin's saying, Bill, in your last example, person and food are treated as underlying types. So there could be some food subtype, which may or may not have that match. If it was being treated as a subtype, then yeah, right. I think you're right. It's tricky there because then that could fall through the cracks in that other idea that I expressed. But were they really underlying types? I mean,
They've gone back and forth in this in the spec. At one point, it was their underlying types. At another point, it's like, no, those are the exact named types that you have to use. I think they're back at underlying types. In that case, you could say, like a more specific example, we could say int comma float 64. And you can say, well, you can't actually pass, if you could scroll down a little bit. Yeah, if we said type int comma float 64, you couldn't actually pass in int or float 64 because they don't have that match method. But you could say, I want to use some of the arithmetic operators common to int and float 64, but I also want it to have a match method, in which case you'd be able to, you're essentially expressing that it needs to be all of those things. And that could be one case, admittedly rare, but one case in which you might want to say, I want these structural, like language intrinsic properties, such as operators, but I also want this special method.
Yeah, I am really hoping that somebody has a simple piece of code that shows a real practical need for this, right? Because even in your explanation,
I'm talking hypotheticals. I can't offer that to you, Bill.
Yeah.
I can't think of a super great, I feel great about that example that it wouldn't be a toy example.
Yeah, that's the problem there for sure. So I don't know, it may end up being taken out. And I think, Kevin, if it does get taken out, then maybe we don't have to do what we're doing to the interface, and then maybe there can be a different mechanic for it, right?
Yeah, maybe. On the other hand, people figure out things after a couple of years of playing around with stuff, and like some killer use case comes around that really depended on it. That's not really how you should design languages. If we need that, we could add it later, but you never know. Like we don't know how people are going to use this yet.
No.
All right. Does anybody else have any other questions or thoughts? Oh, Patrick, go for it, Patrick. Can you unmute yourself, or do you need me to unmute you?
I got it. Hi, everybody. Yeah, thanks for this. I wanted to ask about what if you needed a, like if you had a format stringer, so you had something that can either be return a stringer or a string. How would you handle that? So I wanted a type that could either be a concrete string or something that implements stringer.
You're saying that you want to define some sort of interface that maybe composes on stringer? and then has that same type list? I'm not sure. I mean, you're asking for something like that?
Yeah. And I don't think it needs to be like, it has to be a type string, but I want to be able to create a function that works like print, where it will call stringer if it's not a string, but otherwise it'll just print the string if it is a string.
You want to do conditional logic around whether the method exists or not. The
Kind
best
of,
thing
yeah.
to- yeah, and now you're back to reflection, right? I mean, that's the problem there. This is about you writing a concrete version of code as if T was an int,
Yeah.
but it's not an int. And I think if you needed that support, it's probably part of the emissions. Kevin knows that better than I do here, but right now that's not part of definitely not part of the first release from what I know.
Okay.
I was
Okay,
trying to
just
look
curious.
something up, so sorry I wasn't listening.
No, that's fair. But I think what you're asking for would require maybe some meta programming or something like that. And
Gotcha.
currently they're not looking at that.
Okay, thanks.
Corey, I know you got some thoughts, man. So come on, I want to give you a minute or two. And especially you as a teacher and some other things. So what are your thoughts on all this, Corey?
Yeah, I mean, you did a great job with the presentation, first of all. I mean, you really kind of broke it down to kind of show the current state to the new state. And I think that's very helpful for everybody. I mean, some of the things that I'm still a little torn on, I think where you're kind of just hitting at the end there too, which are, we can use interfaces to get some of this functionality already. Does it need to be a concrete type? And, I think still my biggest concern, and I know they're working really hard on this, is to make sure that we don't introduce some new functionality that people will use in lieu of current functionality, which actually has become, quite well understood, interfaces being part of that. So it'll be really interesting to me to see how they solve that one finally and kind of get that in there, especially with the constraint type at the end you're talking about, right? With that double type syntax. I'll be super interested to see how they solve that. But,
So,
oh, go ahead.
No. What I was going to say is, no, I don't want to interrupt you. You talk, and then I'll.
No, I mean, that's really it. Again, I mean, really where you kind of stopped at your presentation was kind of where I actually stopped reading the draft originally, right? Like I got to that point, I'm like, okay, now I'm seeing some bleed over a little bit from the current spec to the new spec. And that was where, it started to get a little muddy to me. So, but no, I mean, again, I've got some questions on it. I think they're working hard on it. I really do like where they're headed with it. The extra bracket syntax and stuff like that, I don't think anybody's a fan of, but certainly we understand that we need something like that to kind of specify this new type thing out there with the existing syntax. But my biggest fear on that is that Go, from a readability standpoint today, is very readable, right? Like all the functions, all the syntax. Even if you don't know Go, you can almost look at this language the first time and go, oh, okay, I kind of see how this is put together. With the new type semantic in there, it really does add a layer of like, okay, what is this T? What is this, what is this precursor to the function now? Why is that bracket there? And what does that mean? And, it starts to look like the old Windows, like C++ code.
I hear you. And I think it's a matter also over time, your brain will be wired to it. But one of the things I've asked the team, Carmen and Ian and Robert, is that before this gets released, let's say February 22, that there's a bunch of work done in terms of documentation, code examples, idioms, and guidelines, even though they've never done that before, that it's really important that they provide that content. So all of us, whether you're a professional teacher like Corey, or you're teaching every day at work because you're on a team, we can all kind of point to that document and say, well, this is what the Go team says we should do. This is when the Go team says we probably should use, right? So I'm asking for that. It's too early to start putting that together now, but I really do expect that documentation will exist, and that should help with some of the other concerns.
Yeah, I agree 100% about the idioms. I think that the biggest adoption problem Go had ever was that lack of idioms and kind of like explain to people like, this is why Go does it that way. And I think, once that idioms were really out there more, and I think in big part, your training taking off and stuff like that too, and showing the world like, hey, this is how you're supposed to write Go code. And then it makes sense to people. And so if they do that with generics, and show people, listen, this is how you should use generics, and don't leave it to everybody else to figure it out. That'll make a big difference. I think that'll be huge.
Yeah, and they're committed to that. At least they've told me that. So I'm going to expect, and I would also expect that you and others will be involved in that too, right? Because it's going to take a community to do that. Awesome. All right. Thanks, Corey. I appreciate it. Does anybody else have questions / some comments or concerns? Happy, sad? Okay. I know Cameron's waiting at the bit to say something, but he just won't. Thanks, Cameron.
Michael Graff, you have your hand raised still?
Thanks. Yeah. So
Yeah.
I was curious if you could talk a little bit about some of the I don't know what the word would be, like the type inspection you can do with generics. Like, will I still be able to do a type switch, a type assertion, and or reflect?
The reflection package should work 100%. That's not going to be a problem from everything I know. But something that was on the mailing list, actually it's here. I think it was this week. And it's an example. It doesn't work, but they were talking about this. I think it was last week or this week. So I have this example saved because if it ever works, it's interesting. And I think this is what you're asking, Michael, right? So look at this min function where we do a switch on T, because in case it's a float, you may have to do conversions here back to 64 to run math.min, right?
I see.
I wrote this. I didn't put it into the training because I'll give you the link here in the chat because it's just not working yet. And I don't know if it's gonna work, but people were talking about it. So there it is. Kevin, what do you think about this? Because I thought it was
Like
super
whether it'll work or
just even having this functionality. I mean,
I think
there's a practical reason.
having written packages that use reflection a bit, the one thing that like I'd love to not have to write that reflection in the first place, but we're not going to get there anytime soon for certain classes of problems that you need to solve. But the other thing is like, just have trivial little things like a lot of your reflection code is just doing silly, is that a slice, which this helps a lot with. You can say a slice of generic T and then you do reflection on top of that and at least get more of those errors caught at compile time instead of runtime. So I do think, and I would consider this essentially reflection. It's not using the reflect package, but it is doing something at runtime based on the dynamic types of what you pass in. So it really, mechanically, it's still reflection. And so I do think there is a meaningful place for this unless we ever get like an ultra powerful type system that can do all of this at compile time. As usual, I would generally recommend people don't like just jump into this kind of thing as the first thing they try and do. Like don't try and solve your problems this way until you've tried solving it other ways first.
Yeah, but I thought it was super interesting idea where it could be I looked at this more as a type assertion than a reflection, but yeah, I guess
it's type of reflection syntax, the language, the language supports directly.
So Michael, I don't know if I answered your question, but I think this was in line with what you were asking, right?
Yeah, like the use cases I was thinking were basically like, if I wanted to use generics, but then in a certain case reroute that call to actually another function that handles that type in a special way, maybe that, and or like sometimes production code will actually just print out the type, like font dot printf with a %t, just because you want to know what the type you're working with is, and you don't want the generic back at that point. You actually want the concrete type. at
So, I
runtime,
don't
so that
know.
you can see why it blew up. You know.
Yeah, yeah. So I know they were discussing this. This code is obviously not working. I've been hesitant to send it to Ian and ask him if this is even
You,
now. I'm sure I might.
there was a concession in some of the, either it was the latest spec or some kind of Go Nuts post or something, that this kind of thing might be something they explore
Yeah.
as actually doing. I think for right now, if you did a on line 13, if you did it like switch a dot type or a dot like a type switch,
Oh.
that should work. The concession was that
Oh.
since A and B have the exact same type, like I think Ian was talking about this, you should be able to just switch on the type itself, T, rather than any of the specific values. But what the syntax you're trying now should work today.
This a type, even if T is not an interface.
Maybe not.
No.
Well, worst case, you could always say like var x empty interface equals A, and then like
Yeah.
force it into reflection.
Yeah,
It's
I don't
not
know.
great, but
Yeah. So
you'd be able to hack that into something that would work with the Go playground today.
okay. All right. So we see that. I'll look at it. So I've got this waiting in the wings, Michael.
Mm-hmm.
Yeah, Bill, could you send me that
I did. I put it on
playground
the,
share link real quick? Okay.
I did in the chat. You'll see it above Warren's.
Just
Want me
a
to-
quick question, given that it's about this exact example that you put to, if you want to show it again, Bill.
Yeah.
Like, could that math min, could that become a go fix for when generics come in, so that min actually takes its own generic?
Oh, yeah, right. Because there's going to definitely be opportunities to change parts of the standard library as long as there's backwards compatibility.
Yeah, the backwards compatibility thing is actually the wrench, because you can say in your code var f or f colon equals math.min, like you're taking the function itself and using it as a value and storing it somewhere. And that means as soon as you do that, any code that tries to do that, if you demo typing that, yeah, where you're not using any parentheses, yeah. So now the compiler has to arrange for f to have type, especially if you make that as part of like an API contract or expose it in a global variable or something. At that point, f has to have a very specific concrete type. And if math.min is retrofitted to become generic, you can, line 24 isn't legal with the generic function, because you have to explicitly turn it into some kind of type. Now they could change the language to like special case things. There are some special cased functions in standard library packages already. For example, unsafe.sizeof is not a real regular function. It's essentially like a built-in function that just lives in a package. And they could make it so that under certain circumstances, the compiler would allow you to say, eat your cake and have it too. Like if you're using it in a function context, like the f colon equals style thing, it just treats it the old way. But if you're passing in an int, it just lets you get away with it. But historically, Go has not been a language where they wanted to kind of make that magic happen.
Right. And I have a folder in the generics called emissions, where I was able to kind of put some examples that are emitted. And here's that literal function, and kind of tried to find information around why they're saying it, right? So pretty much everything Kevin said.
Yeah, it seems like there's lots of opportunities in the standard lib for generics to be applied, like sort, min.
So
I think that there was some stuff around like node, right? But we're gonna have to have like sort generic if we can't update the update like sort, because like right now there's like sort 64, sort string, right? There's a few types at least pre-created.
Yeah, I've tried to do some of that, like with swapping here and hash table implementation and some other cool things here. And like, what would a concurrency or a channels kind of package look like in the standard library, right? This kind of gives you a kind of a sense. We would need these work functions to make it happen, right? We would need these literal functions, but you could see a general sense of where we could go with concurrency with this stuff. At least I started playing with it a little bit, just to get a general sense of where it could be. So you're right. I like where your head's going there. Plus, I think sync.map, sync.pool would be cool places to get rid of the empty interface. I thought originally that the context could be a place, but I've kind of backed away from that because the idea is that anybody should be able to store value in the context in any sort of call path, right? So I started to think that maybe it doesn't make sense there, but yeah, okay, cool. Who else do we got with their hands raised?
Julian, go for it.
Hello all. Hello, Bill. Thank you very much for this talk. This is my first time in this meetup. Very interesting. I just had a general comment, maybe not a question. The fourth example to me made a perfect sense because it is two very specific types for the user and the customer that share the same method, and we want to make sure that the type is a concrete type. Exactly what you said. The fourth one. Because we are accepting data by what it is, but contrasting that with the sixth example, it doesn't make much sense to me because the type we are accepting is an interface, and that can be done already with the standard syntax in the line 14 of the sixth example.
6 or 5? Because I didn't really go through 6.
No, I just went looking around.
Oh, okay.
The 14th, that V type, that is a stringer, a format stringer, that could be written, I think, already by the standard library in the vals value, could be just an array of stringers instead of having the type.
In this simple example, you're right. You're saying you're saying this.
Yeah, because to me, this the generics thing solves a list of specific types by what it is, but not what it does, because what it does is already solved by interfaces. So this is only valuable to me in the examples when you list out some types, when you have a type list, not a type of behaviors or interfaces.
So I'm going to change this code out now that you called it out, because the real purpose of this code, and something I didn't get to, in fact, I don't even have good syntax here, is to just show that you can have a list of multiple types. But the fact that you spent so much energy realizing that this really wasn't practical in this example means this has to change, because what you said is 100% correct. So I'll work on that.
There is a efficiency aspect to this, which is, well, there's actually two aspects to this. One is efficiency, and another is passing generic values to other generic functions. So for the first one, efficiency, if we made that change of changing vals to a slice of func.stringer, if you had a empty struct type, which takes 0 bytes in memory, or even a bool subtype that either of which implement a string method, those are very small in-memory types. But if you're literally using a slice of func.stringer right there, you're essentially saying, I take your 0 byte struct or your 1 byte bool concrete type, and I'm going to box it into something that is 16 bytes on a 64-bit platform. Exactly the same behavior, Like you won't notice semantically anything different with just this function, whether it's using generics or using the slice approach, except that it will use a lot more memory. If you had like a slice of empty struct that had billions of elements, that takes up no memory, because a slice, you know, billion elements times 0 bytes is still 0 bytes. But with this, it takes 1 billion times 16 bytes. The other thing is to actually use it this way, you'd have to arrange, if you had a slice of this bool type and you wanted to pass it into this non-generic function, you'd actually have to make a slice copy in Go today. And if you expressed it this way in a post-generics Go version, you're essentially saying, I specifically want a slice that can have any dynamic, like each element can have its own dynamic type as long as they all implement that behavior.
Yeah.
But I'm willing to pay the memory and efficiency cost for that. But if you want to express today that you want a slice of stringer types, but the elements all have to be the exact same type, you can't do that today. This allows you to do that, and it also allows you to pass that concrete type for which you might have expressed other properties, such that it's a bool, for example, and thus you can check, like, is it true or is it false? You can pass that into yet other generic functions that know how to handle bools or handle those other properties. So in isolated contexts, yeah, there's not a lot of distinction, but as you start getting more complex code that you're playing with, the benefits start to come out of in strange ways.
So what you're saying is that by putting the interface in the generic type with the V, the only thing we're changing is that we are making sure that every single element in the slice has the same type and not only match with the type. But in that case, why would you be receiving an interface instead of just a list of types? Something like a type list that comply with that method, that specific method.
I guess I don't know what you mean by a list of types.
It would be something similar to what an interface is today. That is a list of methods, but maybe something called a type list that is just a list of types. Because if the only thing that you're checking is that every single piece in the slice is the same type, you could do that with the example that Bill shown with a lot of types separated by comma, but maybe in a better presented way with a struct, something like, I don't know, a type list or something.
I'd love to see an example, kind of like showing that kind of thing. One other fun note is actually with that, if you have fumps.stringer in your generic type list, it doesn't actually, you can still say that. You can still say, I want fumps.stringer as my generic type, yet still pass in a slice of interface types where each element is a different thing, because one of the concrete types that you're allowed to pass in is a runtime interface. So you can you're still specifying behavior in a certain way. As long as you're not in your constraint saying it has to be a non-interface type, you can pass in a slice of concrete types, all the same underlying type, that implement that string method. But you can also pass in literally at runtime a slice of fumps.stringer where each element can have a different underlying type. You usually won't be doing that, but you can do that. So you can have it both ways.
All right. That was all. Thank you, Bill, and everyone.
All right, thanks, Julian. I don't see the raised hands, so.
Yeah, I think Jason has the next one, or the last one so far.
Yeah, my question was kind of just a follow-up of like what Kevin was just discussing in the last question. It seems like there's some advantages to using generics in the performance area, in that you're kind of receiving the concrete type, and you don't have to jump through a vtable or something like that to resolve the method. So you don't have to pay like the runtime penalty of like using interfaces. And there's also benefits of like being able to pass these generic collections to functions. So I guess kind of one concern I have is like, why would we use interfaces? Like, it seems like they have runtime penalty and they have some of these other disadvantages. And the other concern I have is if we implement it as is, what we have today in the proposal, it seems like it might introduce some confusion to new users, and because we have these like two kind of like overlapping features in the language, and they kind of share some similar territory, and it's not clear like to a new user which one should I choose. You know, having some experience in Go, you might be like, okay, well, interfaces are more defining the behavior that you want to receive, and generics are more for defining the types that you want to receive or something like that. But as a new user, you kind of don't really have that kind of history of like using Go to know when you might want to use an interface. So yeah, those are just kind of some concerns I have for new users, like having the overlapping feature set, and then like why would we use interfaces? Are there valid use cases that maybe haven't been kind of demoed here that where you'd want to use an interface over a concrete type? Yep.
So let me speak to the first part of your question statement. Remember how I said that this has not been implemented yet? So it's an important distinction to make because we don't know yet if we don't know what trade-off the language team is going to make here. So we don't know if there is a performance or non-performance gain, or we don't really know if we're going to have a cost like you talked about. And I'll give you an example. The compiler performance is really, really important to the language team and to the community, right? And so they could decide the following. They could decide when they implement this in the compiler that they're going to do pretty much maybe what the transpiler is doing today. Maybe they write out a very specific function and type for every substitution, right? They could do that. Now, if they choose that direction, then we're talking about having larger binaries. The compiler is going to take longer because it's got to write all that code. But we could potentially now have functions that actually use these concrete types. And in some cases, not all, you could avoid the escape analysis causing allocations, right? So you have the potential. But to have code that performs faster would mean trade-offs on compiler performance and binary size. Now they could decide, you know what? We already have generics in Go, right? I said that. Append, new. We already have generics. So what they could decide is, you know what? We're going to keep the compiler speed up, and we're not going to actually have an implementation for every type substitution. We're going to write one function, similar to how we write append in some ways. And now you don't necessarily have functions that are working with the exact concrete type, right? They're doing their, whatever their form of generics is today, which would mean that using the interface or using the generic function would have that same cost at some level, right? And so that's the problem right now. If we get into a conversation about, is this going to perform better? Can we get rid of allocations? What's going to affect compiler? I'm sure they've been talking about it, but right now I don't know if any decision's been made, and I don't know if they've even attempted to implement or prototype either solution. Now the featherweight, what is it? Featherlight, what is that, Kevin? Featherweight Go or something? Featherweight Go document. If you've heard of the Featherweight Go document, I'm going to see if I can find it. A lot of the work that was done on the Featherweight Go, here it is. I'm going to pop this in here. Came back into this, or some of that work that was done in this document here, came back into this new version of generics that I've been playing with. And I think it was this study, I could be wrong, but I think it was a study that maybe identified that we don't necessarily have to write everything out, and maybe the small performance that you take is insignificant or something along those lines. But that's an interest if you want to get a little more academic on all this stuff, because Ian and Robert Griesemer was involved in this, and this really did help influence what you're seeing today. There's interesting stuff there. So we don't know. The TLDR is we really don't know until there's an implementation. Kevin, what do you think?
What they're focusing on is developer wins, not machine wins here. So they're not doing it so that you can have your sum, like your slice summer that just sums up a slice of arbitrary generic types as efficiently as possible. They're making it so you can do that as safely and expressively as possible. Even if they go the second route that Bill mentioned, like let's say they did essentially compiled everything into what amounts to like an empty interface handling function that is a little bit better than the one you can write yourself, but not that much better. The performance on that might not be that terrible anyway. I mean, Java is a language that boxes everything, and the way processors work, they do a lot of branch prediction, they do a lot of, like instruction cache optimization. When you have one function that the processor has to like box and unbox every single thing it deals with, it can actually get pretty fast at that. And that can actually sometimes be faster than having 150 different functions that have to get loaded into the processor instruction cache. Like takes a long time to load it in, then it goes really fast once it gets there, but then you have to unload it and load another one. Like it's hard to predict how performance works anyway. So I don't think we should be too dogmatic, as Bill is saying. I agree with him. We should not be too dogmatic about what direction it takes behind the scenes. I think the developer wins will be the biggest part of this. If you really need that performance, you can just copy paste. You can use Go Generate. You can copy pasta your code anyway to get the specialized versions of your code. And generics just essentially saves you from having to do all that in the typical case. And most code out there that you write in Go is not computing pi. It's doing a bunch of IO work where like the difference between 3 nanoseconds and 15 nanoseconds is not that much.
Yeah, yeah, I'm totally understanding of like the fact that none of this is like implemented in the compiler yet. So we don't really know what the performance characteristics are. But like given that like it's kind of even more ambiguous, like which one you should choose if you're like a new user, like would you choose generics or would you choose an interface?
Yeah, I've got
So,
an
like,
example for, you asked the question, is there a use case for interfaces now that we have generics?
Mhm.
And yeah, there are
Okay.
cases where you absolutely need runtime dynamic behavior. Imagine you write a reusable work queue, like a task runner that takes data in on a channel. It takes like a work function in on a channel, schedules it, maybe arranges for all the data it needs to be there, etc., and then actually runs the function. It would be one very boring task worker implementation if you have to instantiate a separate like worker pool for every type of data that you want to process. So that's the kind of thing where you'd still want to have a channel of runtime dynamic things, essentially based on function methods rather than like intrinsic type properties, like it's a bool or it's an int or it's this specific type of struct. And you can mix and match. You can still have runtime interfaces based on like generic methods, so that you can say I have a work method that maybe takes an int, which is like a job ID, but it takes some generic other type. It's still a method. It can still be implemented by different types at runtime, but it still has some generic properties that you can still use. So I think the answer is going to be, there will still be cases where you absolutely want runtime interfaces, because there are certain things you literally cannot do with generics at runtime. But we'll still probably start to see it gravitate more of a hybrid model, where even your runtime interfaces have some aspects of generics baked into them. Like one of the parameters in your method is a generic parameter.
Thank you.
I like that. I like that example, Kevin, where you don't want to have to construct a new entity for every type. that we just construct that once, and then it's the method set of behavior that's driving what that code is doing, right? So I really like that thought and idea.
And let's be clear, like interface polymorphism via interfaces is strictly a more powerful language feature than generics, because it does allow you to do runtime variable behavior that you cannot do with generics. Are just really good at letting you be expressive at compile time, but they don't do anything to really help you be expressive at runtime.
Right. Awesome. All right. Anybody else want to express a thought, opinion, have a question? These were great questions, by the way. Thanks. So let me do something, and Warren, I'm going to put this in the chat one more time, but maybe you can publish this when this is all done as well. I just really want to make sure everybody has access to that Google survey link if they want to share anything with the Go team, give any feedback.
Yeah, I was planning on putting that on the Slack channels, and I think I'll even put it on the YouTube description and stuff like that, if that's helpful.
Beautiful. All right, I think if that is it, I really appreciate everybody's time tonight, and it was great to see Corey and Kevin. I know these guys from way back and haven't seen them in a while, so that's kind of nice. Other than that, then I think we're good, Warren.
Yeah. All right. Thank you very much, everybody, for attending. Thank you very much, Bill, for the talk. It was really awesome. I had got some comments offline saying that even though they are new to Go, it was very digestible and structured, sort of format where, just as it kept on building, they could keep understanding. So thank you very much for that. I'll definitely be trying to share the word. And as soon as I finish the recording, I'll post it on YouTube and post that YouTube link on Slack. And yeah. I'll reach out on the Denver channel in Slack if you want to reach out to the organizers, if you are interested in giving a talk or have a topic about what you want to learn more from. Awesome. All right, everybody, with that, I'll stop the recording. Thank you.
Thank you, Bill and Corey, for
Thanks, everyone.